gas mixing and initial depth calculation. In this presentation we'll cover gas mixing from an empty gas quad and from a gas quad that has already holding pressure. We'll also cover chamber pressurization gas to use for saturation blowdown. It's called an initial depth calculation. Gas mixing is a skill that you will need to apply when you are working offshore as a sat diver or as an ALST. Large work sites usually have gas recovery systems and blenders and premixed gas, but basic gas mixing skills will still be needed by you and will be covered in this presentation. Also in this presentation we will cover chamber pressurization and initial depth calculation. You'll be required to perform this calculation when you perform as an ALST on this course, and you will be tested on it. Okay, the gas mixing formula, the general gas mixing formula looks like this. Pressure of mix 1 is what we're trying to establish. So it equals the final pressure multiplied by percent final mix minus the percent mix 2 divided by percent mix 1 minus percent mix 2. And when we're making the two gases in an empty quad, mix 1 and 2 are mixed together to give the final mix. The percentage of the final mix must lie between the percentage of mix 1 and mix 2. Mix 1 is the richer mix, or the most oxygen. Mix 1 is pumped first at the lower pressure. Now, a note of some importance is for mixes over 21% there is a fire risk. That's something we have to be careful about. We try not to mix high oxygen. We use this formula to find out the initial pressure of the first mix. Now the gas mixing triangle, which we'll cover, is based on the above, and it may be easier. Some people find it easier to use. Example. You've got an empty quad, you want to make 200 bar of 9% using 2% and 12%. What pressure of each gas do you need? There's a formula, we've already covered that. We're looking for the pressure of mix 1. So let's look at the numbers here. We've got 200 bar, final mix is 9%, mix 1 is 12%, mix 2 is 2%. So there's our formula again. We need to plug in the numbers, 200 by 9 minus 2 and 12 minus 2. So that gives us 140 bar of 12%. So you need 140 bar of 12% and 60 bar of 2% to make 200 bar of 9%. Okay, let's do the calculation using the gas mixing triangle. 200 bar of 9% required, so we use 2 and 12%. Okay, there it is, triangle method, 200 bar of 9% required, use 2 and 12%. Step 1, write oxygen percentage at each corner of the triangle. Put the mix you know the pressure of at the top. So we know we're going for 9% and we've got 12 and 2%. That can be on either side, it doesn't matter where you put it. Step 2, write the pressure that you know inside the triangle opposite the mix with that pressure. So you know it's 200 bar, so let's put that between the 12 and the 2. And that is below the 9%, which we are looking for. Step 3, subtract the small figure percentage from the larger figure percentage and write the answer between the same two percentages along the side of each triangle. So look at the bottom there, you can see that between 12 and 2 we've got 10, okay? And you can see between 12 and 9 we've got 3, right? So 12 minus 9 is 3 and 9 minus 2 is 7. I hope that makes sense. Okay, step 4. Divide the pressure by the figure underneath it. In this case, that is 200 divided by 10, which equals a factor of 20. Multiply the factor by the other figures as shown. So just look at the diagram there. We've got 200 on the bottom, divided by 10 gives us 20. Now if we look at the top left, we've got the 7 there, right? So we multiply that by 20, gives us 140. Place that inside there. Do the same on the opposite side. Okay, so write 140 inside the triangle. Do the same on the opposite side, that is 60. Reading the opposite corners shows that you need 140 bar of 12% and 60 bar of 2%. Remember, the percentage figure at the corner of the triangle goes with the figure on the opposite side. So there's our answer. You need 140 bar of 12% and 60 bar of 2% to make 200 bar of 9%. Okay, it's rare to have an empty gas quad or a gas empty cylinder. So mixing usually involves pumping gas into a partially full quad. In this case, turn the formula around to calculate final pressure. So looking across at the example there, we've got 100 bar of 4% and you want to turn it into 10% by pumping in 20%. What will the final pressure of the mixture be? So there's all our figures there. They're the values. And then we look at the formula, you can see it's changed slightly. So we've got pressure of mixed 1 instead of final pressure. Okay. Just a note on the left-hand bottom there, mix 1 is whatever is in the quad, and it may not be the richest mixed. If it's actually the weakest mix, negative numbers will appear in the calculation and they will cancel out. Okay, so let's look at the formula. We've got 100 bar is the pressure of mix 1, and we're multiplying by 4 minus 20, that's percentage mix 1 minus percentage mix 2, and we're dividing it by percent final mix minus percent mix 2. And that gives us that formula you can see with the orange writing next to it, minus 16 and minus 10. Now those two minus signs can cancel out. So if we take away the two minus signs, that gives us 100 times 16 divided by 10. Okay, that gives us 1600 divided by 10 equals 160 bar. So that tells us pump in 20% until the pressure reaches 160 bar. So we're going from 100 bar to 160 bar with 20%, or a little over to allow for cooling. There's our answer. Okay, let's look at the triangle. You've got 100 bar of 4% and you want to turn it into 10%. Pump in 20%. What will the final pressure of the mix be? Step 1. Write oxygen percentage at each corner of the triangle. Same as before, we put the mix, the pressure at the top, which is 4%, and 10 and 20 on the bottom two corners. Step 2. Write the pressure inside the triangle opposite the mix with that pressure. So we know the pressure is 100 bar. We're going to put it in between the 10 and the 20 there. Step 3, subtract the small figure, the percentage, from the larger figure, the percentage, and write the answer between the same two percentages along each side of the triangle. Okay, so there we are, subtract a small figure percentage. 20 minus 4 gives us 16. We've done that before, so that's pretty simple. Step 4, divide the pressure by the figure underneath it. In this case, that is 100 divided by 10, which equals a factor of 10. So look at the bottom centre. 100 divided by 10 gives us a factor of 10. Now multiply the factor by the other figures as shown. So we've got 6 multiplied by 10 gives us 60 on the left there, central left. And on the right we've got 16 minus 10, which gives us 160. Okay, now look on the right hand side of the drawing here. We need to write 60 inside the triangle and do the same on the other side, write 160. Now reading the opposite corners shows that the pressure of 10% will be 160 bar. This is achieved by pumping 60 bar of 20% into the existing 4%. So our answer is pump 60 bar of 20% until the pressure reaches 160 bar, or a little bit over for cooling. It'll take you a little while to get your head around this. Just have a practice a couple of times until you get it. Okay, gas mixing and initial depth. Now we're going to talk about something else. It is actually gas mixing, but it's inside the chamber with the people inside the chamber. And we call it the initial depth calculation. So this is what we have. We've got a target depth. We're going to 90 metres. We want to get 600 millibars when we reach there. We want a PPO2 of 600 millibars or 0.6 PPO2 bar. And you have 18% and 2%. What is our initial depth once we start blowing down? So that's the question. I'll read it out aloud. The chamber is to be pressed to 90 metres using 18% and 2%. The final PPO2 must be 600. What depth of 18% should be added at the start of the pressurisation? Now there's our calculation. I strongly recommend you write this down somewhere and try to memorise it. So we're trying to find the depth of the rich mix, or initial depth, some people call it. So what we have to do is we've got a PPO2 required in millibars, which is 600, a PPO2 present in millibars, which is 21 or 210 millibars, which is air in the chamber. We have 21% in the chamber. We subtract by the depth times the weak mix. The depth is 90 and the weak mix is 2. So divided by percent rich mix minus percent weak mix. Let's look at the numbers. 600 minus 210. And 90 times 2 and 18 minus 2. So bringing it down a bit further, we've got 390 minus 180 divided by 16. Bring it down further. 210 divided by 16 equals 13.13 metres of seawater. So we're going to start the pressurisation by adding 13 metres of seawater of 18%, then carrying on to the bottom depth 90 metres with 2%. The divers in SAT will then have a PPO2 of 0.6 bar or 600 millibar on arrival. Practice that a couple of times and you'll get the hang of it. Here's another one. The chamber is pressed to 60 metres is to be pressed to 60 metres using 21 and 2%. Final PPO2 must be 500 millibar. What depth of 21% should be added to the start of the pressurisation? There's our calculation, there's our numbers, and there's the breakdown, and it comes to 8.9 metres of salt water. So starting the press by adding 8.9 metres of salt water of 21%, and then carrying to the bottom depth of 60 metres with 2%. The divers in SAT will then have a PPO2 of 0.5 bar. Or 500 millibar on arrival. Have a practice of that. You're going to need to get good at this when you're doing this on the barge. In summary, for gas mixing and initial depth, there's two ways of doing the gas mixing calculations. One is remembering the formula on the left. That's most likely the one you're going to use because you're nearly always going to have gas in the cylinder or in the quad. And then that is the formula you will need to memorize. If you have trouble memorizing it, you might find it easier to use the triangle, the gas mixing triangle. And lastly, the chamber pressurization or the initial depth calculation, you're going to have to try and remember this. So try and write it down and memorize it, practice it a couple of times. It is very accurate.